All right, I just want to go back through this problem a little bit and hopefully clarify a few things. I kind of rushed it in class a bit, and so I'm just going to walk back through it and then actually solve it. The same math, but with a little bit of a different illustration. So there's your given statement. If you miss class, you can jot all that down. But a big part of this was the point that you kind of have to filter your input information in order to see if it's practical or not. And in this case, the big thing was we're given an allowable velocity, but that doesn't necessarily mean that we're going to hit that velocity. And then the visualization of that would be if we do get to the maximum velocity, then we may have to dwell at that speed for some amount of time before starting to decelerate. So in that case, you'd be speeding up, moving at constant speed, and then slowing down. If we don't hit that velocity, then we're basically just speeding up, and then when we get to the maximum speed that we do hit, immediately start slowing down. And the reason for that is just the problem statement. It says do this as fast as you can, and dwelling when it's not necessary at a given speed is always going to be slower than accelerating and then decelerating as fast as you can. So first thing we did was just kind of look at it from the point of view of checking that 8 feet per second. It's like, can we actually get to that? And the question there is it even possible to reach it in 48 feet? And then I kind of looked at it that way. So is it possible to reach velocity of 8 feet per second and 48 feet at the initial acceleration? And of course, you do have to then slow down. So even if in this study I find that I can reach 8 feet per second in less than 48 feet, that doesn't mean I can also slow down. So checking to see if you can reach it is kind of a first step. It may be the only step necessary, which happens to be the case here. So for this, how long to reach 8 feet per second? We're just using that form of the kinematics equations, and we find it takes 13 seconds, a little more. And then one more equation lets us figure out that it actually is to distance-wise to get to 8 feet per second, we'd be at 53 feet. So we're actually past the point where we want to have sped up and then slowed down. So if we can't even get to 8 feet per second in 48 feet, then we certainly can't get to it and then slow back down. So that very specifically indicates that the maximum velocity reached in this problem is going to be less than 8 feet per second, and that means that the velocity profile is going to look like it does in the second figure there. Now, as far as illustrating the problem from there, we're basically starting from a ground plane and then going upwards. So we got our ground plane down here and all the motion up above. So what I did in this one is just kind of lay out the series of events and give them whatever values are known, and then label the unknowns as well. So get my highlighter again. At the ground, we know we're starting from 0, and I'm basically just saying that that's going to be my reference point as well. So position is 0 and speed is 0. At the end, we're going to be at 48 feet in the air. And again, we're coming to rest, so velocity is also 0. At some intermediate point, somewhere between 0 and 48 feet, we have to stop accelerating, start decelerating, and that's going from an increase in speed to a decrease in speed. So basically, we've hit a maximum velocity somewhere along this travel path. Don't know what that value is for velocity yet, and we don't know where it happens, and we also don't know the time it happens in, which in this case would effectively be T1. But we know it has to happen. So we're speeding up to a maximum velocity in time T1, and then we'll be slowing down from a maximum velocity in time T2. So the total time, which is the problem question, is T1 plus T2. Now I can work from this diagram, but just to simplify it a little bit more, let's break it into two separate motions. We got motion 1 and motion 2. And starting with motion 1, I'm just going to again write down everything that I know about it. That being that in our initial location, velocity and position are still 0. Acceleration is 0.6 feet per second squared, and that's true over the entire motion up to our intermediate point. And we're starting at time is equal to 0. Then when we get to the point of maximum velocity, well, velocity is a maximum. Position, I'm calling position S1, and our time is equal to time 1. Now in the second motion, you've got some options as to what you use as your reference for both time and position. Here I'm setting position equal to the initial position equal to 0. I could actually set that equal to S1, and in that case, my position at the top would be something slightly different. So by starting it at 0, I can just give it an arbitrary S2 designation at the top right here, and that's fine. But I could, and let me just write this in a different color so it stands out. Let's just go with red. If I were to declare my initial position here to be equal to S1, the same coordinate system I used for the whole thing, well, up at the top, I could still call it S2, or I could actually call it, I could call that 48 minus S1. I could do that too, because I know the total is 48, and I'm starting from S1. So there's different ways of framing the problems, but in this case, I'm just going to set my initial position equal to 0. And then our final time would be T2. All right, got our acceleration. Acceleration in the top portion is negative because we are slowing down. I kind of defined in the initial statement vertical upward to be positive. So the acceleration is going to be going downward, indicating a deceleration. That makes it negative. So we've got the negative 0.3. All right, so the unknowns there would be still Vmax. Mark them. Vmax is unknown. T2 is unknown. T1 is unknown. S1 is unknown. And S2 is known. So we got to look at a relationship between some of these things and see what falls out. And from here, I'm basically doing what I did in class. I just kind of framed it a little bit differently, but hopefully this is a little clearer because everything's laid out. So from that expression for velocity as a function of position, we can take all of the information. Let me start down here. We can take all of the information that's in our diagrams and apply them to the equation. So we are solving for the maximum velocity. That got out of hand or off the page, but right there, maximum velocity. Our initial velocity is 0. Our acceleration in this portion is 0.6. We're going from 0 in terms of position to S1. So solving for all of that, what we get is an expression for position S1 as a function of the maximum velocity. And if we repeat that in the top portion, our knowns and unknowns are slightly different. In this case, the initial velocity, that's the biggest difference, is the maximum, and then it's going towards 0. But we still solve that out and get an expression for S2. So now we've got those two expressions, and we know that S1 plus S2 has to be equal to 48, so that's the total distance. From that, we can solve for velocity. Now all we've got left to do is solve for time, and we'll just use one more of the constant acceleration equations for that, that being this form. And we're inputting the same information that we found in the diagrams, right? So our initial velocities, our final velocity, and accelerations in order to solve for time. In this case, of course, now we know Vmax so that we can directly solve for time. So to get to maximum velocity takes 7.3 seconds. To decelerate back to 0 takes 14.6 seconds, and that gives a total time of 21.9 seconds.